Hello everyone. So today we will be seeing the MATLAB simulation perspective of the communication system. So last class we saw some of the MATLAB simulation commands, like how can we simulate the random variables and their distributions, and then it comes to communication systems. So here we will see some of the power spectral density and the basic communication system. Then we will go to the simulation. So basically, the objective is like to simulate the simple communication system and estimate the bit error rate. So system characteristics is BPSK modulation. This is a single carrier modulation. Uh, so single carrier in the sense the carrier will be single only. And if we say in 5G we have OFDMA, so that is OFDM, that is multi-carrier. There we will use multiple carriers for the modulation. So here the single carrier where the bits will be represented only in terms of 1 or -1 with the equal priority probabilities. Okay, then we will use some raise cosine pulse, by raise cosine pulse to transmit the information, like suppose this is 1, so this is 1, and if it is 0, then it is 0, then it is 1. Okay, and this is also -1. So 1 0 or 1 -1. It can be anything. Raised cosine pulse have their own benefit. Why we use raised cosine pulse instead of this particular triangle or this particular square? Why we use only raised cosine pulse? Because raised cosine pulse have Fourier transform of rectangular. Okay, that is fixed bandwidth. That is fixed bandwidth. But if we say the Fourier transform of this rectangular pulse, then it is a thin function. That is in practice we have bandwidth of 1,000. That is not possible. So that's why we use raised cosine pulse to transmit. Because if it is used in the time domain, the raised cosine pulse, the frequency domain transformation will be finite bandwidth. So that's why we use raised cosine pulse. Okay. Then simple AWGN channel that we will see how to modulate it, how to simulate in MATLAB. Okay. So then we also use some oversample integrator and dump receiver front end and digital masked filter. And we will also measure bit error rate as a function of ES by N naught and oversampling rate. Okay. So the system to be simulated is like the first thing is what is baseline equivalent system to be simulated. So this is like a bits that is coming uh, to the input. Okay, now we will modulate it. Why this is delta t? Because the Fourier transform of this is cos 2 pi fct, right? Then only the summation will be delta t. Okay, the cos 2 pi fct, what is the Fourier transform? If it is AC cos 2 pi c, AC by 2 to AC by 2, this is minus fc and this is fc. Right. And here we are talking about a time domain to satisfy. Cos have the frequency transformation in terms of impulse. So that's why it is multiplied with respect to impulse, summation of impulse, because two impulses are there. Okay. Now this will be converted to pulse. Now after multiplication with cos, it will be converted to pulse. Because here we were talking about that pulse. Right? I did made it here. Pulse. That is raised cosine pulse. It is pulse. Now it is again multiplied or amplified with respect to amplification. Okay, so it is multiplied with respect to A. Then this ST will come. Okay, this ST will come. That will what will be the ST? ST will be Bn summation of del T minus NT. Then multiply with A, so A. Then it is again added with the channel, that is noise. Then it is this signal will be transmitted to a again a function which is pi ts. It is a sampler, and the sampling frequency will be there, fs, and finally the rn will be transmitted. So what this is what this is a time domain signal. So here up to this point, this is time domain. Okay, this is time domain and continuous. Now, T is equals to NTS if we multiply. So, what it will come? It will become digital. That's why digital signal processing, then we will go to this RNS digital signal. Basic baseband equivalent system is there. Then from continuous to discrete time, the system in the preceding diagram cannot be simulated immediately because most of the signals that are continuous time signals cannot be represented in MATLAB. So that is one of the issue that in MATLAB. Then possible remedies is we have to rely on sampling theorem and work with sample version of the signals, or we have to consider some discrete time equivalent systems, or the second alternative is preferred and that will be pursued below. So that's why we have to go through the sampling theorem, work with sample versions of the signals, and we have to then consider discrete time equivalent system. Then we will see what is discrete time equivalent system. Okay. Towards discrete time equivalent system, the shaded portion of the system has a discrete time input and a discrete time output. So this is a discrete time input and discrete time output because here we can see this is discrete or this is also discrete. Can be considered as a discrete time system, and a minor problem is input and output operate at different rates. So that is a minor problem that we will see how to resolve it. Now, discrete time equivalent system is it is equivalent to the original system and contains only discrete time signals and components. Okay, we will see. So input signal is upsampled by the frequency of FST to make the input and output rate equal. Why? Because here we were using the sample rate of TS. Okay. So to make the input and output the same, so we will multiply our upsample by Fs into T. Okay, and the output is equal. So if we have to insert, what we have to insert? We have to insert this FST minus 1 because that is a basic definition of upsampling. So upsampling means that if it is sampled by particular rate, so the uh, the rate minus but zeros will be inputted between the input samples. Okay, so I hope up to this it is clear. Then we will move ahead. So this is what like we have to upsample. So we have these things matter actually if we see in simulation as well. So the components of discrete time equivalent system is question. What is the relationship between the components of the original and discrete time equivalent system? So we will see this is PT, this is ST and 2 DSP. So discrete time equivalent impulse response we have if we see. So to determine the impulse response HN of the discrete time equivalent system, so we have to set the noise NT equals to 0, set the input signal BN to input impulse signal. The output signal is impulse response. The procedure yields that this is convolution of input to output. Okay, because at the end we are having HT as output and PT as input. This is HT and HN as output. So Hn equals to 1 upon Ts, Nts to n plus 1 Ts, Pt convolution with HTDT. Because this is what it is an impulse response. Okay. And the input signal is Hn, del n. So that's what this del n, Ht, and this Nt. So for high sampling rate, FST that is very, very greater than 1, the impulse response is closely approximated as Hn is equals to Pt convolution with Ht where n plus 1 Ts. Like it will be convolved at every n plus 1 by 2 Ts. Discrete time equivalent impulse response. So if we see, so discrete time equivalent impulse response, if FST is equals to 8, so this will be looking like this. Now, discrete time equivalent noise. So to determine the properties of the additive noise, the discrete time equivalent system will be set input signal to 0. Let continuous time noise be complex, wide, Gaussian, and power spectral density is N naught. So the power spectral density was taught in the class. I hope it is clear. So what is a power spectral density? So power spectral density, autocorrelation uh, x, z. So is it correct? What is power spectral density? So yeah, power spectral density was related to our to correlation function, and this power, that is MSV, is nothing but autocorrelation at zero. Power spectral density, if we see the formula, so formula is this, wait. So P is equals to power spectral density into bandwidth. So PST is equals to P divided by bandwidth. And this is, if we put the autocorrelation as zero, so PST is equals to RXX0 by bandwidth. Also, we have formula in terms of, so I will do it because that is very important. We have to understand what does it mean. So as we know, what is energy and power? Okay. So if we see the energy of random variable x, okay, so it is equals to 1 upon 2 pi minus, why 1 upon 2 pi? It can be 2 pi without 1 upon 2 pi also. Agree? Very true. Why? Because here I am using dw. So that's why 1 upon 2 pi. And if we do use df, so it is minus infinity to infinity. So let's go ahead. Except, okay. And this is like, and the power spectral density is Fourier transform of autocorrelation function. And if you put Rxx is 0, that is the power, that is MSV. So using that power spectral density also we can calculate, but it is actually the Fourier transform of autocorrelation function. And if you ask what is autocorrelation function, and if you say what is Px, so Px is 1 upon 2 pi minus infinity to infinity Sx of x dw. The area under power spectral density is area under power spectral density autocorrelation. So I will tell you again. So what I was talking about. So energy and power. So energy and power. Now the question arises, for which signal we calculate energy, for which signal we calculate power. So energy is calculated for non-periodic signals. What are non-periodic? Which doesn't repeat after certain period of time. Okay. So we have, suppose, non-periodic signal that is finite. So it is calculated for finite signals. It is calculated for finite signals. Okay. So energy का formula क्या है? E of x is minus infinity to infinity x of w square dw. What do you think that is it equals to time domain? Yes. If we calculate power, energy in frequency domain and time domain, it will be same. So this is xt square dt 1 upon 2 pi, and that is also equals to minus infinity to infinity x of f square df e of x. Okay, this is energy, and that is calculated of finite signals. Okay, but the thing is, what I want to say, This is calculated for some finite signal and non-periodic signal. That way I have given the definition. Now, what should be the energy for a periodic signal then? Since this is finite and this is calculated for finite signal, so what will be the power? What will be energy for power signal? Do you know what is power signal? So first of all, let's decide what is power signal. So power signal which is periodic. It's also called power signal. Now periodic signal in the sense is xt plus t is equals to xt. Okay, which repeats after certain period of time, where t is time period. So the power is calculated for infinite. So do you think that whether the periodic signal will be finite or infinite? It will be infinite, obviously, because it is repeating. Infinite and periodic signal. What is the formula? What is the formula? So the P of X is, since this is periodic, so it will be 1 upon T. Integration upon 1 upon T. Integration over 1 over time period T. Then X of F square df. Or it can be also calculated in time domain. So 1 upon T. Integration over T. X of T square dt. So can anyone name me what is the theorem name? Power calculated in frequency domain and time domain is same. What is theorem name? What is the theorem name? Very famous name.
Parseval theorem.
Yeah, very good. So it is a Parseval energy theorem or a Parseval power theorem. So Parseval power or energy theorem. It states that power calculated or energy calculated in power time domain and frequency domain is same. So what was my question? This is the power and energy formula that I have told. But what was my question is what will be the energy for power signal? So answer is infinity, because it is calculated for finite signals and the power signals are infinite because they are repeating. So the energy calculated for the power signal for any power signal. So energy for cos 2 pi fct, that is a main carrier signal, is infinite. Sine 2 pi fct is infinite. Now the question arises, what will the power for energy signal? Since the power is calculated for infinite signal, the energy signals are very finite, like ut. Suppose some triangle signal is there. This is not repeating. Then some square signal is there. This is triangle, this is square. So energy power calculated for these signals is 0. Okay. So this is energy and power. Now I was talking about autocorrelation function and power spectral density. So autocorrelation is what? Autocorrelation Rxx of tau. Nothing but expectation of x of plus tau multiplication with x of t. So this is autocorrelation function. Like it is finding the expectation of x t plus tau multiplication with xt. Okay, and if it is as autocorrelation with tau, then it is x1 and x2. Then x1 t plus tau multiplication with x2 t plus t. Like the difference should be tau. T plus tau minus t is tau. So that's why tau. Now, if we do the Fourier transform of this autocorrelation function, then it becomes power spectral density at omega is equal to 0, obviously. Why omega is equal to 0? Fourier transform at omega is equal to 0. Why? Because then only it will give the area under that. Okay, so what is the power spectral density formula then in that case? What is the power spectral density formula? This is a Fourier transform. So x w, because I am talking about Fourier transform. So this is minus infinity to infinity r x of tau e power minus j 2 pi f t dt. Okay. Now this is power spectral density. Okay. Now if we ask what is the power contained in that signal, the power contained or the power contained random variable or in any distribution x, this is px, can be calculated from minus infinity to infinity x of w dw. That is the area under power spectral density is the power. So this is the area. Area under power spectral density is power. PST. This is the basics for power spectral density, autocorrelation, and the density. Last class we saw like what is random variable and how their distribution looks like, and why we only talk about the uniform distribution. Because if we do the transformation of random variable, then we can have any type of distribution from the uniform distribution. The transformation works perfectly in case of uniform distribution. That's why whenever we do in MATLAB simulation, just we have to type first x is equals to rand of any type, any size. Suppose rand, it is giving n cross. So n cross n value of 0 to 1 it will give. Okay. So we do uniform distribution and we will see how to map the transformation of random variable that we saw in the last class. Okay. So what we were talking about, this power spectral density was taught by Sir also in the class. Now, noise samples. So you may wonder like how can we have Gaussian noise also in simulation? So in MATLAB, there's very common terms that is used in MATLAB simulation, but also we can have the transformation of random variable from uniform distribution. Okay, but that will be specified by mean and the variance. So that you don't have to worry. Now we will go to the receive simple energy. Well, the last entity that we will need from the continuous time system is the receive signal per symbol. Now you may wonder like why we are talking about the symbol. Because whenever we transmit the data, you are not transmitting the data bit by bit. You're transmitting in a group. And the group of bits that you are transmitted at one time is called symbol. Okay, so that's why in QPSK you have the symbol that contains of two bits. Okay, and you have different 8 PSK that you will have the symbols of 3 bits. Similarly, you have 16 PSK will have the symbols of 4 bits like that. Because in that modulation you can have the constellation diagram differently. Okay, so if we say QPSK, you have the constellation diagram like this. You will have each symbol will contain 2 bits, but if we have 16 PSK, we'll have, and each symbol will contain 4 bits. So in that case, the constellation diagram for the different digital signal is different. Okay, so this is like simple energy per symbol we are calculating as an ES. Okay, now the ES is controlled by adjusting the gain at the transmitter that we saw in the basic block diagram. So to determine the ES, we have to set the noise ET as 0 and transmit a single symbol BN. Okay, because at one time we are transmitting one symbol. So we have to compute the energy of the received signal as RT. The procedure is that E is equals to sigma square A square integration of PT convolution with ST. Now you may wonder why this is coming. Okay, so ES is what? Energy contained in one signal. A square was multiplied beforehand during the transmitter only. And sigma square is what? Sigma square is variance of the source. So that is also multiplied. And why PT convolution with ST is multiplied? Because this is the output that you are getting. This is the output you are getting. So as for the formula of energy is what? It should be square. So this is like PT convolution with ST modulation with the square, like mod of square dt. Now this is the formula of ES. Now for BPSK we consider the sigma square S is 1. For the system under consideration, this is basically A square T. Now, yeah. So this is what this is like. This is coming to 1. Now the area under dt is T. So this is A square T. This is PT convolution with STY. I'll show you again. So yeah, output is what? PT convolution with ST multiplied by A. So this is what it is going as output, XT, right? That's why it is PT, A is here, convolution with HT, right? And if we square it, so A square will come out, PT convolution with HT. And later we will find that this is also equal to 1, but the area under this is actually T. So A squared T as ES. We will see how this is actually going to work because PT is actually the pulse function. Okay. And the pulse will be 1 for one time duration. Okay. So if we see simple the signaling diagram, so it will be 1 for one time duration. So it is 1 into T area. Okay. Because integration is nothing but area. Okay. Okay. Now we have understood the basics of communication system. What is a basic block diagram? What is multiplied? And what is the energy contained in a symbol, one symbol? Okay, and the input was a BN. Now we are in position to simulate the transmission of the sequence of symbols. Now only one symbol will not come. Sequence of symbols will come. Then only you will transmit the message. Because if the message is huge, you are dividing into symbols. And at one time, one symbol will go, then after the other time, other symbol will go, and it's a time sequence. Okay. Now the MATLAB functions previously introduced will be used for that purpose. So we will proceed in 3 steps. First of all, we have to establish the parameters described in the system that we have seen A, PT, ST, BN, all those things. Now we have to then we have to parameterizing the simulation. Other scenarios are easily accommodated. Okay, so simulate the discrete time equivalent system because continuous time systems were not possible. Then collect the statistics from the repeated simulation. Okay, we will start now. Simple set parameters. So this is a script that sets a structure named parameters that to be used by the system simulator. And what are the parameters? So this modulation. What is this name? This is used for commenting. So you can see, and if double uh, division modulator you will use, so you can have the script. So you can make it as a script. So we have to construct the structure of the parameters that to be passed to a system simulator. So these are the communication parameters. First of all, T, that is a symbol period. So that is 1 upon 10,000. Okay. Then what is the samples per symbol that we were using while converting the XT to the XN? Okay. I hope you remember. The final output was RN. Then we have to normalize this receive signal to 1. So that's why we will see how we are normalizing. Then ES over N naught, that is signal to noise ratio, ES by N naught, that is 6. And if we have the alphabet as that is we are mapping the every symbol to either 1 and plus 1. through raised cosine pulse, that is +1 and -1. And the number of symbols is 1000. Now, the discrete time equivalent impulse response, which is the raised cosine pulse, but the FST is equal to parameters plus FST. And we will see uh, from where to where. Okay, so 0 to FST -1 will be created at an interval of plus by 1 by 2 divided by FST, and the parameters dot HH is nothing but square root of square root of 2 by 3 1 minus cos 2 by dt s multiplied by sine pi by FST divided by pi FST. This is a discrete time equivalent that we are doing for this set of parameters. Okay, the parameters you can take, that is not a problem. But TTS, like T is equals to NTS. Remember? So TS is nothing but 1. Here the TS is nothing but 1 upon FST. Okay, so that's why TS is 1 upon FST. So this N is created using this, and TS is 1 upon FST. That's why this is 1 upon FST. Okay, so by in MATLAB, you know that this will create 0 to FST -1 samples with an interval of 1 by 2. This is array actually. But again, you have to multiply by TS, so that's why 1 upon FST is multiplied here. So actual simulation is carried out MATLAB function MC simple, which has the function signature below. The parameter set in the controlling script are passed as an input. The body of the function simulates the transmission of the signal and the subsequent remodulation, and the number of incurred decisions that should be determined to have bit error rate. Okay. So this is a function like I have already explained like how can we have the function definition in MATLAB. So this will have two output. Okay. MC simple is the function name, and these are the parameters that we give as a input. Parameter struct. Okay. Simple set parameters. These are the parameters. Now, simulating the discrete time equivalent system. So, simulation of the discrete time equivalent system uses a toolbox function that is random samples, linear modulation, and add noise. Okay, so this is transmitter gain square root of ES by T. That A we saw no A square T was a ES. So this is actually ES was A square into T, right? So A is what? Root over ES by T. Okay, because ES and T are defined previously. Okay, now if uh, okay, yeah. So simulate the discrete time equivalent system. The transmitter and channel via toolbox function. So in MATLAB, we often use toolbox function. And the gain, these things like if you want to have depth over this, like why we are taking N naught as a noise PhD, because this N naught is not nothing but the power spectral density. Okay, so power spectral density is E and not, and ES by over and not is already defined. So it is defined over above. So ES by N naught. So this is actually giving to N naught. So that's why N naught. Noise variance is nothing but N naught by T multiplication with FST. Then scale. We have to scale that with the HH and HS dash gain through the signal chain that we were doing that before. Okay. Now, if we have to simulate a discrete time equivalent system, transmitter and a channel via the toolbox function, the symbols equals to random symbols, where it will go from n symbols, alphabet, and priors. Okay, and the signal is nothing but the A multiplication with the linear modulation. Uh, Linear modulation is actually giving the symbols HH and FST. And if it is real, so signal will be generated. It is equal to the complex one that ensure the signal is complex valued also. And the received will be the simple add noise signal plus noise variant. This is a basic communication system that we are going through. Okay, so digital match filter was not taught in the class. So I'll be going to share my screen for the digital modulation in the MATLAB. I will share. So we will see here. Give me a second. Just give me a second. It's loading. Okay. So we will see here the step by step because I think that was going over your head. I don't know. So we will see through the actual simulation. So, okay. So in this activity, you will simulate a simple back-to-back communications link that uses quadrature amplitude modulation, and you will generate a source signal of random
The
bits
screen is not
modulate.
visible.
Hello?
Your screen is not visible.
Again, is not visible. Okay. I have to just give me a second. Why it is not visible? Is it visible now?
Yes, ma'am, it's visible.
Yeah. Yeah. So we will see here uh, in this activity, we will simulate the back-to-back communication links that uses a coordinated amplitude modulation, and you will generate actually a source signal of random bits, and it will modulate the source bits using COM, and also demodulate using COM back into bits, and compare the demodulated bits to the source bit if they are matching or not. So basically, this is a basic uh, block. If we can see, we have the source bits that is coming in the form of bits 1001, and then we have transmitter. That transmitter is actually the antenna, and that antenna itself is a modulator. Okay, the modulator can have different modulation. The COM is there, it is a quadrature amplitude modulation. Then we will pass it through the channel. Then we will also have demodulator, and finally the receive signals. Okay. So we will go through the task by task. So this is very basic. So I have started like this. The first step in any digital communication system is to create a source signal. So here the source signal is a sequence of bits, or in MATLAB term, we can say the vectors of 1, 0. So we can have, you can use the randi function to create the column vector of randomly generated zeros and ones. So we have, if we want the integer, so you have to use randi. If we want only 0 to 1 continuous value, so you can use rand also. And so 0 to 1, okay, we have to generate, and this is number of bits into 1. So first is like this. Let's say under the number of bits. Okay, we have to first define number of bits. So let's say number of bits is how many bits it is not written here. Let's say 10. So it will generate 10 bits, column vector of 10 bits, 0 to 1, 0 and 1, it will have 0, 1, 0, 1 and 1. So number of bits cross 1. So this is a size and this is this one between 0 to 1. Okay. The second input is the first input sets the range of 0 to 1 and second is the number of rows and the columns. The output X is the column vector containing number of bits. The task is create a column vector named source bits containing 20,000 random generated bits. Okay, so this is actually our task. Let's do that. Source bits is randi. We'll see from very basic, so don't worry, we will go to the advanced also. So here 20,000 is there, 20,000, and since this is one cross only, so it's not required. First, we will see, is it doing that? Okay, we'll see something. So next task is 16 com is actually a single carrier modulation and it maps 4 input bits to the one of the 16 complex numbers called symbols. So what does it mean is like we have 16 symbols like it's cross cross that I was making in the constellation diagram, but every cross has having 4 bits. So that's why total is 16 numbers. Okay, that is also called the symbols. For each, so 4 input bits to one of the 16 numbers it will map. So which is called symbols. Okay, so one symbol will consider 4 input bits. So for each complex value symbol, the real and imaginary part present in the space and the quadrature components respectively of the waveform. So every symbol will have phase and the phase and the quadrature in phase or a quadrature components. So that will represent real and imaginary. If it is real, so it is in phase, and if it's imaginary, it is quadrature components. So the 16 in the 16 com is a modulation order, and it is useful to store the modulation order in the, to be used throughout the simulation. So let's say modulation order is equal to 16. This is task 2, 16,000. Okay. Now QAM mod function creates a modulator. So this is a inbuilt MATLAB function that we will use. So it is creating the modulated QAM signal from an input signal. So this is what it is creating. So y is equals to QAM. Okay, so this is COM order. So that the modulated signal Y is a sequence of COM that is having the bits. So we have 20,000 bits and modulation order 16. So every 4 bit of 20,000 bit will be modulated to one of the 16 symbols. So it will be modulated in such way that, and also when the input sequence is made of bits, the set type is input type to bit. So we have to use that. Because we have modulation order as input type and bit and X. So we have to use source bit, right? So we are also having source bit. So try to remember some of the things. We have COM modulation that is already used. Modulation order is the second input and input type is bit. So I hope first let's see in output. Y. So yes, very true. So what is happening here? 20,000 is mapping to 16 symbols. Okay, so if you divide 20,000 by 16, so what is the answer? Calculator 20,000 by 16. So it's 5,000 cross 1. Wait. 4. Okay, so sorry. 20,000 by 4. Create a 16 command signal for the bit sequence name modulated symbol. Achha, sorry. Mod out. So first of all, 20,000 will be divided into 4. Okay, so 5,000. Okay, correct. So 20,000 will be divided into 4. So that's why this is 5,000 cross 1. Okay. Now you can look at the constellation of the modulated coamp signal that we have. I mean, we will see how its constellation works. So we will see by using the scatter plot. Okay, this function plots the imaginary part as a quadrature versus real in phase of the each complex variable comp symbol. So this is like 20. First of all, we started with 20,000 bits. Then it is mapped. Every 4 bit is mapped to because com is there. So every 4 bit will be mapped to one symbol. Okay, so that's why it is divided by 4. That 5,000 plus 1 came into the picture. Now let's plot this. Okay, scatter plot odd out. Okay, let's see. So here 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 16. Okay, so 16 symbols are there. So this is in phase and quadrature. That is correct. System is a little slow. I don't know. Yeah, it is correct. So the next task is what you see in the scatter plot is the ideal 16 com constellation. So 16 complex valued symbols arranged in a square with each symbol equally spaced from its neighbors. You can see the spacing is same, and the greater the separation between points, the better is the error rate performance. So why this is possible? Why we want greater separation? Because this will not collide with each other, so the the possibility of error will not be there. So that's why the error rate performance will be less. And later when you add noise to the simulation, you will see that the received observation depart from its ideal configuration, and that's why the noise comes into a picture. For now, the simulation assumes the modulated signal is unchanged when it's received by the receiver. So change the variable name change out and see it is variable name, create a variable name cha out and set it equal to the modulated. So let's say mod out. So that is a simple thing that they have asked. Sam out and mod out. Like they're saying, let's say we have this is the output without adding any noise. Then we will add noise. Okay. Now in the receiver demodulation turns that 16 quam symbols back to the bits. Okay. Now the simple demodulation works. Okay. But we haven't add now noise here to make sure that mind this. Okay. We have to use the chord cam demod function to demodulate the receive signal. It has almost the same syntax as QMAT. Okay, so the only difference is output type as bits. Okay, now we have to demodulate the signal and demodulate the receive signal chain out because this is a receive signal that we have received without addition of noise. And let's add demod is equals to if you write by yourself, you will remember. Okay, form demod. It's very simple. Then what is chain out? Like this is output. Then modulation order is mod order. I think that is only variable we have used. Yeah, mod order. MATLAB is very easy to understand. It's very playful that you can learn the things and read. And this is the course that I am going through. That is also given by MATLAB on ramp. You guys also can go through it and look into it. I can cover some perspective. So yeah, so this is coming demodulated receive signal. So let's say whether this is correct or not. It will definitely be correct. Okay, we will add noise now. Since the 16 com signal was not subject to any channel effects, the receive signal should match the bits exactly. So let's see whether it is matching or not. To see if two vectors are identical, we have to use this check. So the source big it's matching with check or not. So check is equals to is equal SRC bits was there. You can use tab. It will definitely cover that our thing. So that was above one as demod. Let's say whether it is matching or not. We have to check. Yes, logical is Yes, it is matching. Because we haven't added any channel. But if we add, we will see that as well. If we add, it won't match. Because 16 comp maps the inputs bits in a set of 4, the number of source bits must be the multiple of 4. Try changing the number of bits in the source signal. And what happens if it's not multiple of 4? What can we do? Okay. So since we have taken 20,000, let's say we are taking 21,000. So what it is happening? We are again running it. Okay. We are again running it. Again running it. See, equal symbols are there. That is correct. We are again running it. I want to see check is equal is not. Yeah, again running it. Now we have to check where it's equal. Again it is equal. So how it is mapping? So we have to first check 5 to 50. So what is there? So if we divide 21,000 by 21,000 by 4. So again it is a multiple of 4 only. So sorry. I have to check something which is not multiple of 4. Okay. But let's say. So yeah, it is showing error. When input side is bit, it is showing error using form validate. So we can't use actually the number of rows must be equals to number of columns. So again, you can check the intersection. Okay, we will see some more adding. What will be the effect of noise? Okay. Now the common corruption, which is also called noise source in the received signal, is due to electron motion. Now you may order often misunderstand like what is noise. Sometimes you think that noise is an external effect that you are transmitting and adding, but no, noise is by default present in every electronic device due to electron motion. That's why it is called additive white Gaussian noise. And why it is additive? Because it is adding. Why it is white? Because it is affecting every frequency of the particular spectra of the particular signal. So if you see the electron motion, that is by default, it is not the interference. You understand this. Noise is different from the interference. The interference happens externally, but the noise is through the electron motion that is present in the devices or the transmitter or the receiver from the electrons or the electronics in the receiver. So that's why this can be what is a channel, but sometimes channel may be seen from the external perspective of interference. Okay. The noise is called additive white Gaussian noise because it is typically added to a signal. It has flat or the white spectral density and it has Gaussian probability density function. And if we say why Gaussian, so from the Monte Carlo distribution, we saw that if you add any signal, say let's say triangle, rectangle, any signal, infinite number of times, the signal that you'll get after infinite number of times is Gaussian in nature. So that's why every signal that you assume by default is Gaussian. Also, one of the main thing is if you see the Fourier transform of Gaussian in time domain and if you see the Fourier transform of Gaussian in frequency domain, it is same. Like Fourier transform of Gaussian is also Gaussian. Okay, so it is not even affecting the frequency domain. Okay, so that's why it is Gaussian. Now you will in this activity you will add noise to the 16 comp link simulation. Here you will have AWG and noise. Okay, let's see. That is This is like number of is 20,000, moderation at 16, create space, it is creating. Okay, so what is that? The AWGN noise applies additive white Gaussian noise to its input signal. The amount of noise added is specified as a signal to noise ratio, assuming that the input signal has the average power of 1. We will see this is average power of 1. We can have different power as well. Uh, Now, fortunately, you can tell the com mod function to output a signal with average power of 1. Simply set unit average power to true, or we can have sig out. We can have,
Excuse me, ma'am. The
yeah, yeah.
Fourier transform is used for converting a signal from frequency domains to time domains and vice versa. Is
No, no,
it the
no.
significant?
Fourier transform is used for converting frequency domain from time domain to frequency domain, and inverse Fourier transform is used for the vice versa.
Okay, okay, fine. Thank you.
Yeah. So we have to create a 60 QAM signal from the bit sequence SRC bits and specify the output signal to have unit power average this power S1. So pick mod out. We have to use properly. Mod out is supposed to mod or it's SRC bits. Let's write by yourself. SRC bits. Then we have to give mod order and input type as input. Let's say it is writing. So see here you will also get in your MATLAB also. You will have so much of help like I am also getting. So again the unit power average. See here you will have so many other things also. You can have so many other things. But here we are only having two. Okay. So variable name we have to take care. So I think I have to do some. Mod out, I haven't written correctly or what? Mod out or mod SRC bits, mod order. SRC bits is not there. It's SRC bits is there. Input type bit unit. I don't know why it is wrong. C mod or solution. So solution is SRC bits, mod order, input type bit, unit average power through. Correct only. Cob order, mod order, where I have written wrong, I don't know. Somewhere I have kept wrong. Or unit average power as true. Let's say display log command multiple.
Semicolon is missing.
Haha.
Semicolon is
Semicolon is
missing.
just to that was missing. I knew. But semicolon, I think that should not be semicolon actually if we are doing using semicolon, it will prevent from printing. That is the only difference. Still we can try with semicolon because we have to check for others also.
We did not specify the input type. What type of input we are using? Maybe there is
They
some
are
value, zero or one input type.
bored out. Input type is bit only, right? It is correct only. What again we will copy what it is there in the solution. Sometimes it happens. Okay. See, this is a solution. We should do by ourselves only. See, SRC bits, com out, mod out. What is difference? I couldn't see anything. This is different. Mod out. Or mod. Let's see. This. Correct. I don't know. There's some glitch in this software, but it was exactly same, like whatever we did. Now we have to add the noise by applying AWG into the modulated signal. You can use the AWGN function to apply AWGN to the signal. The signal noise power is actually specified as signal to noise ratio. So let's first define SNR, signal to noise ratio as 7. Suppose it is written there. Sig out is actually signal to noise ratio, signal plus SNR. So this is like the noise power added is specified as signal to noise ratio. So this will be added AWGN to a signal of SNR value of this thing. To define a variable named SNR with a value of 15, so this is a task. Apply AWGN to modulate a signal with SNR. So chan out, this is channel out as AWGN mod out. Yes. Okay. Then we have, let's see the scatter plot. And, definitely, we will have some shift in the signal, the symbols. See how much shift it is. So it is actually, you can see, due to noise of order 15. So if you want to decrease also, you can decrease the strength of the signal, noise power that is added. But yeah, see, the effect of noise. And that's why at everything we are decreasing the effect of noise. Now you can see the noise has perturbed the symbols from their ideal values itself. The comp demod function uses the nearest neighbor decision rule to map, like, because after adding the noise you have to use demodulation also to have the receive signal, right? Because at the receiver you have to get whatever signal that is transmitted. So comp demodulation uses the nearest neighbor decision rule. So this is also known as MLP. So maximum likelihood, I think this is not maximum likelihood. This is nearest neighbor decision rule to map the receives observation back to the nearest ideal symbol constellation point. If an observation has been perturbed too much, it will map to a wrong point. Definitely, the effect of noise will be more. So this results in symbol errors, which is leading to bit errors. So since you set the unit average power when you called, you must also set in the comp demod. Okay, so let's see. Uh, demod chan out and the demod out is equals to comp demod. Then we have chan out, and then we have a mod order, obviously. And we have input type, input, input type, output type, sorry, it will be output type. So this type of mistake we don't have to do. Sometimes I also get confused. So this is bit, obviously. Then you have unit average power. This is, we can copy it from here. Okay. So yeah, and we have also check. So the next task is check whether the source bit is not matching or not. So name the result check is equals to is equal source bit SRC bits and demodulation का output. Let's first run this, whether this is running on. Okay, logical is 0, definitely. To view the result, leave off the immediately. Okay. So again, we can see output is 2000 cross 1 only, but some of the bits may have mapped to different one. This time the source bits and receiver bits do not match. Try increasing and decreasing the value of SNR, and how does it impact the scatter plot? We can see some of the values, like let's say 6 dB. So it will have some effect. Okay. See, all of the things are mapped. Why? Because SNR is in negative. If it is SNR values are always in negative. So if you are increasing in positive sense, so if you want to decrease the SNR effect, so you want to increase it further. Suppose 17 dB. I can have 35 dB as well. So this is in dB. See, so if you have more SNR, you will have less channel effect. Okay. So the source bits are randomly generated. So each time you run the script, it will be different. How do large they have to set SNR for the source and receives able to match consistently? Okay, you can do a quick check to see if your link is operating correctly without noise, but by increasing SNR to a larger number like 100, this effectively remove the noise power signal. So it is very useful to know how many bit errors are there. That is big difference between 5 bit errors and 5,000 bit errors, right? In the next activity, we will found the bit error and calculate the bit error rate. So we will see some of the bit error rate as well. So if you can see, if you increase SNR too much, like 100 or something, so it will not have the noise effect. So noise can introduce errors in the received signals. Comparing each bit sent to the corresponding bit received tells you if there are any errors. The fraction of bits that contain the bit errors is key way to measure the performance of any communication system. Source bits and the receive bits. Okay. So simple is like we have already done some of the things. There are only 2, 3 tasks. So to count the number of bits, you start by performing bit by bit comparison of the source bits and the receive bits. So this logical operator compares the two elements one by one. Is error. The output is error is a logical array that has value 1 where the elements is not equal to 1, and we can actually sum it and we can find the number of bit that is an error. So compare the source bits. So is bit error is equals to SRC. It's we can have not equal to, that is D mod. So how many months are there? I think it is not visible here. So non-zero. So number of errors we can have, the number of non-zero in a particular array. So N and Z will represent a number of particular number of arrays. Number of bit errors N and Z is bit error. So then finally we have to divide with number of source bits. So oh my God, 84 out of 1,000 to 20,000, it is 84 in the bit error due to 15 dB of noise. Okay, so we have to, the bit error rate is calculated by dividing this number of bits. So BER is number of bit in errors, number of bits. What was the thing that we have used? Number of bits. So 0.042. The BER of 0.042 means that 43% of the received bits do not match to the source signal. Try increasing and decreasing the value of SNR on line 9. How does it affect the BER? Right now, the transmitter output is a sequence of clock signal, but to transmit a signal over a real value signal, you need a time domain signal. Okay, so what we are doing here, we have just the bits. Okay, now we are modulating it, we are adding noise, and we are demodulating and we are getting the received signal. But in practice, we also have real-time signal, that is a real-time time domain signal. It is not simple in bits. So actually we need a time domain signal. So the pulse shaping filter converts the sequence of symbols into the time domain signal using a weighted regularly shaped pulse. So that's why I was telling like why we used raise cosine pulse, and that is also the pulsed shaping filter converts the symbols of sequence of symbols into time domain signal using weighted regularly spaced pulses. In the next activity, you'll add pulse shaping filters, so the transmitter and the receiver. I hope this is like
BR should be 0.4%, I think.
yeah, what?
0.042 BR means 0.4%.
Yeah, actually it is
Oh,
written wrong there. If I divide what
0.4, I
was
think.
86 divided by 20,000. It is 0.4%.
And we are getting 0.042.
We are getting 0.042, then it is 4%. Yes, yes. Not everything it is written correct only, but we can see through set of problems and yeah.
Fine.
Why filter a signal? This is a very small introduction. I not should have not included any filtering. So here we have source bits. We have source bits. Now filtering was not included, but actually in practice we also have filter during the modulation itself. That the phone. So you ever wondered, like in phone, how many antennas are there? So in 5G phone, the antennas are 5 or 6. Okay. For every antenna, that is a transmitter. Okay. That antenna is nothing but a transmitter. It's very, very small. Okay. Why antenna size is small? Because we are doing modulation. And the modulation is affecting that is the antenna size is small. Now the antenna is having the modulator. Along with it, one small transmit filter is also there. So that's what we have the continuously shaping continuous signals, and but that modulator along with the modulator transmit filter will also be there. So one of the basic reason like why we are using transmit filter, because every antenna or every signal is having the particular band. So if the band is affecting the other band, okay, so it will have the interference. The transmit filter will make sure that the band of particular signal doesn't go beyond that particular band of other signal. For example, if we say the car, so if the one car is working in one lane and it is going to the other lane, and but that lane is dedicated for the other vehicles, so it will affect it will interfere the vehicle that is working in that lane. So the interference should not happen. So transmit filter will make sure that that interference doesn't happen. So, as we know, the function of transmit filter, similarly, the function of receive filter will also be there. But in receive, we also have the noise component. So that's why the receive filter has one more function, that it will also reduce the power of the receive signal, like the power of the receive noise signal. So it will reduce the power of receive noise signal. But since these two filters are working for one communication system that is happening, so for example, one speaker, and it is transmitting, also receiving at the same time to some audience. So it will have transmit and receive filter both. So in that case, both should match to a single frequency, because we have to maximize the signal to noise ratio at the receiver. So that's why these two transmit filter and receive filter should have matched filter capability. That is also called matched filter, that we will see and simulate in the MATLAB. So in this lesson, in fact, sir also taught the raised cosine first. So we will be using raised cosine first, raised cosine filter for the transmit filter and the receive filter, and they are matched also. But what if these two filters are not matched? So you can see here in the figure, the one symbol is there and the next symbol is there. So one symbol, if it is not matched or it is like one beside that, so you can see one everything is smeared down. So it will get distort the information at the same time. But if we say the raised cosine pulse, the raised cosine pulse do not interfere with each other. Why? Because the peak of one raised cosine pulse is coming to the zero of the other raised cosine pulse. So even if they are combinedly transmitted at the same time, they will not interfere to each other because the peak is not interfering with each other. Peak of one symbol is actually coming to the zero of other symbols. So that's why raised cosine filter is often used in transmitter and the receive filter. The Now we will see in action. Raised cosine pulse are actually very important filter that we are also using. In this activity, we will add root square raised cosine filters to transmitter and the receiver. Why root square? Because whenever you transmit, the power is square of that. Okay, so that's why root square. The power is MSV. So the root square square will be normal MSV. Now the transmit filter takes a 16 form signal as input and its output is sent to the channel. The receiver filter takes the channel output as its input and its output is passed to the form demodulator. Okay. So here the transmit filter and the receive filter is there. Now, because systems typically use match filters, it is common to create the transmit and receive filters at the same time. Okay, we will create at the same time. You can create the square root raised cosine transmit filter using the following syntax and the similar syntax for the match receive filter. Okay, it should match actually. So we can have transmit filter and receive filter like this. These syntaxes set the filter properties to default values. If you leave off the semicolon, you can see some of the properties in the output panel. For example, let's comp dot. So comp dot raise cosine transfer filter. So yeah, it's having the properties as a shape as a square root. Role of factor is 0.2. What is the role of factor? The factor which is going down. That is also called alpha. Filter span in symbol 10 outputs. This is like by default values that is kept here. Okay. Now, for example, the property output samples per symbol, samples per symbol is this one, 8, has a default value of 8, which means that the filters upsamples the signal so that it has 8 samples for each comp symbol. Okay, so basically, if you have here transmit, so transmit will have the capability of upsampling, whereas receive will have the capability of downsampling. Why we are doing upsampling in case of modulation and downsampling in case of demodulation? Because we want to transmit the amplified signal so that it sees the channel properly. But once it reaches the channel, we have to also reduce the effect of noise. So that's why the receive will have the property of downsampling. Okay. Now, what is the task? Create a square root raised cosine transmit and receive. Name the transmit dx and the receive filter. To display the filter properties, you can leave up the semicolons. So actually, there are two TA classes that is happening for the So here we can see output samples per sample is 8 and decimation input samples per sample is 8. That is an input and a filter in samples is 10 and decimation factor is 8. That it will decimate by 8 and gain is 1. So actually, I want to tell you one thing like there's two TA classes that is happening simultaneously. So one is happening in this Friday, another is happening through me, that is Saturday. So the Friday classes, I am seeing that the most of the questions and everything, whatever taught in the class, she is dealing at that. But then I have left with no other questions to do that. So that's why I'm teaching it this particular way so that we can have more physical understanding of wireless communication also. But yeah, if you have any doubt of the questions also, we can take that as well. And I have also prepared the questions for that. The last 10 minutes, we will see the questions. So to apply the transmit filter to the modulated 16 QAP, we have to do sig out. So transmit filter is this, the modulated mod out. This is already mod out. So transmit filter out. We will see the filter output also. That is what. So this is the filter output. Size will be same only. That we don't have to take care. Now we have to, since it is after the transmit filter, we have to again apply this AWG. Notice that the transmit filter is 8 times longer than the mod out. Okay, so because it is a upsampled. Okay, so upsampled. Uh, which is expected given the value of filter property output samples per sample. Next, you want to apply the AWGN to the filter signal. However, the transmit filter change the signal power. Okay. See, now the signal power will change. So we can't use the same signal power. Okay. To scale the noise power appropriately, pass a third input to the AWGN function. Now, we can use the word measured option. The function calculates the input signal power and scales the noise power based on that. So, SNR is given as, let's say SNR is 7 dB and churn out is AWGN. SIG is what? Transmit filter out, right? Out, set out. So this is a churn out. I think it is correct. So since after applying filter, we have to use measured also because then only it will have the signal power appropriately because it is again upsampled by 8 times. Now apply the receive filter. Then after churn out, the receive filter will be there. So let's say receive filter out Rx filter out is equals to Rx filter churn out. Yeah, that is it. So we have also seen the raise cosine pulse significance through set of activities. Remember, you added more noise to the channel here, SNR of 7 dB compared to the previous activity of this one. So here you can see if you are adding uh, less positive values, so it is more. Okay, the receive filter has reduced the noise power by about 8 dB. So you can see the receive power is 8 dB because you are added more noise. Okay. Now, the receive filter, so the constellation has roughly the same amount of noise as a signal from the previous activity. Okay. So receive filter is actually doing the same, reduce the power by about 8 dB. It can be useful, helpful to view the signal spectra of both noiseless filter signal and noisy signal. To do this, create a spectrum analyzer that displays a spectrum of two signals. So how we can do with the spectrum analyzer, you can look the spectrum of the transmit output and AWG output. The noiseless is yellow and the noise is blue. Let's see this. Spectrum analyzer is actually, it will create in another window. Variable spectrum analyzer. First of all, we have to define spectrum analyzer. Oh, that's great. So channel 1 and channel 2. So what is this? Uh, with the spectrum analyzer, you can look the spectrum of the transmitted filter output and the AWG and channel output. So what was yellow and blue? Huh. You haven't explained it to do this time. The noiseless signal channel is yellow and the noisy signal is blue. So you can see the noisy is blue and noiseless is yellow. So how you can see noiseless, noisy? Because see, everything it is added, the values are added. So this is noisy and this is noiseless with different frequency range. This is spectrum analyzer. We can see different spectra. So what we have seen first, we have seen a transmitted filter output. Okay, channel 1 transmitted filter output. Then after channel, that is after this one, we have the channel output. That is blue. First is transmit filter output and is blue. That is correct. So this is actually good enough to see and observe. Now filter delay is also there. So transmit and receiver filters incurs a delay on the signal, which must be accounted for when the two-bit sequences are compared. So source bit and delay, receive bits, this should be compared with a delay. So how we have to check? So for each filter, the delay is half of the filter length. Okay, in symbols. So you can extract the filter length by accessing the filter span in symbols properly, then divide by 2 to give it a delay. Okay, so the delay is the sum of transmit and receive filter delay. To calculate the total delay, uh, by summing the transmit and receive delay in symbols. Now we have to check also because the filters are delayed. So how to compare the bits? You need to determine the delay in bits, not in symbols. So we have checked only in symbols. Okay, now we have to check in bits also. So say 16 4 bits are mapped to one symbol. So this conversion factor, give me a second. Just so sorry. Huh. So for 16 the 4 bits are mapped to one symbol. This conversion factor has been stored in the variable bits per symbols defined in the script. So we have seen 4 bits and this conversion factor has been stored in the variable. So this is bits per symbol, log order 2. That's very correct. If we have 40, we have 32, then again that will be different. Okay. So delay in symbols will be simple. Delay in bits is, so for basics, we are just going through it. After this section, we will go to the questions. So exact align bits. So now that you know the delay, you are ready to compare the bits. To compare the correct bits, you need to align the matching bits from the source bits and the received bit sequence. So this is source bit that is aligned and the received is the delay. So we have to just check the delay. So how we will check, we'll see. First, get the aligned bits from the source bit sequence, delay in bits, by extracting all but the last delay in bits. So first get the aligned bits from the source. So we have to only check after last the source bits, source aligned. I know you, I hope you know this. Like it will go from 1 to n minus delay in bits. So this is the array, so it will only have that source aligned is equals to. So next, get the alignments from the receipt. So you are removing the alignments after the transmit one, but the receive will be added in front, okay, prefix. So we have to get like this, to demod aligned is equals to demod out. So it's very correct. Like you are what you're doing. So you have to just start with +1 because delay +1 because it is starting from 1. If it is 0, then again you can go from that. But the MATLAB starts from 1. So again, I'm writing it. This is array, subarray containing delay in bits +1 to n. Okay. Now we have aligned, okay? Source aligned and demod aligned. So just what? Non-zero, what is not equal to? So we have to just get that number of bits array after removing. So how it is working? First of all, we have the race cosine filters. Then race cosine filters also want to have the same frequency. So we masked it. Then we remove the delay because it is adding a delay. Race cosine first is adding the delay at the end in the transmitter, whereas it is adding the delay in the receiver. And it is simples are divided by 2. The delay in the simples are divided by 2, but it is again multiplied by 4 because that is multiplied order of modulation order. So like this, we are doing it. So try to remember some of the things. Then only will understand the communication system. But by doing, you will understand. Not a problem. Uh, source aligned not equal to keyboard aligned. So there's a number of bits. Now task 3 is number of alignments. So BER is what? So the line bit stream is shorter than the original. To calculate the bit error, you need to divide the number of bits by the aligned bit. Okay, so then again, just BER is equals to divided by length source aligned. Okay, that's correct. So BER is 0.0017. Remember, you used a much lower signal to noise ratio when you added filters, and the bit error rate is still low. But try changing the value of SNR to see how it impacts the BER. Okay. Further practice if you want to see this. Again, it will be same only. Let's see. Yeah, it is. So actually, in practice, the many wireless communication doesn't exist with line of sight. So we will also have non-line of sight communication. So the transmit signal receive the receiver after so many reflections or through so many obstacles. So the reflection which results in a multi-path path. So we have to model that also. It actually means the transmit signal has traveled the various multiple paths before reaching. So every path is actually modifying the signal in different way. So it can modify the signal in the amplitude basis, or it can modify the signal in time basis or the delay basis. But we will use the multipath signals in MATLAB as an impulse signal. So we will see a multipath channel model in the next section. And I think 15 minutes left, so I will just cover the questions. So we can see this in this activity, we'll add the multipath channel to a simulation. The multipath channel precedes the AWGN because the multipath is actually encoded at the AL. So this is like before AWGN, this is multipath channel modeling. So before adding AWGN, we will have the channel modeling. And before the signal reaches the receiver that adds AWG. Okay. For simplicity, you will simulate the static channel. However, in scenarios where transmitter, receiver, and reflectors are moving, the channel impulse response is also time varying. So we will see why the channel impulse response and how the multipath channel is affecting. So this is very good section that we will see, I think, mostly in the next class. And I'll just cover, give me a second. So I hope these PPTs we will see in the next class also, like why the digital match filter and why we have also use digital match filter output and input MATLAB simulations. So this was the last time assignments. Which of the following statements is true? All the entries of the random sequence are randomly distributed. A random sequence becomes a deterministic if the experimental output generating is known. The entries of a random sequence are necessarily independent of each other, all of the above. The random sequence are identically distributed, correct? The random sequence becomes deterministic if the experimental output generating is known. Actually, the entries on the random sequence are necessarily independent of each other. So answer is second, random sequence decay determinacy, because third is not correct. Third is not correct because it is not necessary that it should be independent of each other. You can't even make sure that it is independent to each other. So if we see the solution side, the random sequence becomes deterministic in the because general note explanation. All the entries of random sequence are identically distributed. This is saying not necessary to. A random sequence can have entries that is not identically distributed. For example, consider the sequence of random numbers where the first half is drawn from the uniform distribution and second half is drawn from the normal distribution. So this is correct. This is not this. A random sequence become deterministic if the experimental outcomes and is not. If this statement is true, because if you know the exact experimental condition that the parameters in generative sequence, you can predict this value with certainty and randomness allows for the certainty. Okay. And this was not correct because they can have independent entries. The mean of a random process is also a random process, a random variable, a constant, a deterministic function of time. This one. The mean of random process. What is random process actually? What is random process? The function of random variable. When a random variable becomes function of independent physical quantity, then random variable turns to random process. So when the random variable x, that is a mapping from omega to real line, okay, when x becomes the function of t or some temperature or pressure, then it becomes random process. The mean of the random process are definitely deterministic function of time. Now we are only talking about time. So deterministic function, again, it is the mean of a random process denotes the beauty is indeed a deterministic function of time because it represents the expected value or the average value of the random process at each specific time point t. The mean function is not random. Why? Because it is determined solely by statistical properties of the random process and rate. Random process, therefore, it is it doesn't vary with different realization on the process. Therefore, it is determined function that characterizes the central tendency of the random process as a function of time. Now, the auto-covariance function of a random process xn is defined as, please tell me. Answer will be third or second, third. Yes, we'll see here. The autocovariance function of a random process xn is denoted as this one, has a statistical relationship between two different points, and this is this one. The autocovariance function is defined as, this is the definition of the function that we can't change actually. This x e of x n 1 x star n2 minus e of x n1 e of x star n2. So basically, this is what the e term current definition represents. This term represents the expected value of the production of this one, and this is representing the product of the expected value. It accounts for any potential offsets or the biases in the random process at time indices n1 and n2. So I think so, covariance. It's even you have to remember this because even if it is not related with anything, you have to remember this. Uh, this is what E of n1 multiplication star of n2 minus E of n2 n1 only multiplication star of n. See, the random process is called stationary in the wide sense. When the CDF is independent of the time, regardless of the order, is it? No. The mean function is independent of time. Actually, it is little correct, but not correctly properly. the correlation function is independent of time. It is also correct, but little correct. Actually, both of these two should correct. Let's say fourth, both the mean function and autocorrelation function are the independent of time. So basically, random process, which is a function of time. When the random process, suppose this one is a process. Okay, this is xt. Okay, and this becomes stationary when it is constant. Like if x of t is equals to x of t plus tau, means it is constant for a particular time. So it is called stationary for this particular time. Okay. So that will be called stationary for that particular time. So this means that mean will be constant and correlation will be also constant. Why? Because let's break the CDF and you can see this. I will upload these things. The Gaussian process can be completely characterized as mean and autocovariance. Correct? Because Gaussian function is already written in terms of what? 1 upon 2 by sigma square e power minus x minus mu whole square by 2 sigma square. It is represented in terms of what? Gaussian, mu and sigma, right? The power spectral density of a random process is, we already saw Fourier transform autocorrelation function. Correct. One and third, let's square of the absolute value of the Fourier transform. No, 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 not the square. It's a power, but not autocorrelation function. See, we saw this Fourier transform of Rx of tau. Given that the power spectral density of WSS frequency and this is equal to power spectral density is given this is equal to power or mean. Second variance. Sorry. Power is characterized by variance. So sorry. So this is actually power, which is equals to variance. A random process is called white. Why? Why this AWGN is white? Because PSD is flat. So it's flat. Okay. Okay. So it is white because power spectral density is flat. In other words, the power spectral density is constant and is equal to all frequency. This means that the first process has equal power across all frequency components. The PSD doesn't depend on frequency. If the flat PSD implies there is no correlation between frequency components and each frequency component is statistically independent of each other. That is called the white noise, and it is actually different for random process to be noise. Okay. So I think we have covered most of the things in today's class. And if you have any doubt, you can just mail me also sometimes. Thank you, Nidhi and Kirtana, for staying till this point. And I hope both of you are appearing for the exam. Nidhi, have you registered for the exam?
Ma'am.
You haven't
Because
registered.
don't have any knowledge of this electronics signals.
Whoa, from which branch you are?
Computer engineering.
Uh-huh.
Computer engineering.
Computer. Computer engineering. What motivates you to take this class or the course?
I'm doing PhD in communication networks.
Oh, very good. Okay. So yes. So even if you are doing PhD in communication networks, you should have knowledge of MATLAB and physical layer that is taught in this class, in this course. So it's very good, and it's good that you are doing that. But you should have little concept in signal system. If I say, for that you can refer some good books, that is open and hand. You can refer that book. At least you should understand Fourier series, Fourier transform. Once you understand that, you can cover this course. That is not a problem. So, because if you understand the Fourier transform, then you can relay the things. But yeah, even if you're doing PhD in computer networks, you should have some knowledge of physical layer. That's very good. Like, have you done your master's?
Yes.
Okay, from where you are looking to do PhD?
I am currently pursuing PhD from NIT Kushetra, Haryana.
Acha, acha. Okay, 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 okay. That's great job. You can have understanding. Are you appearing for the exam?
I'm not registered yet.
I think yesterday was the last date. I am not sure. You can check actually if you want
Third is
to
the last.
appear. When is the last date?
3rd August.
No, no, no.
Yesterday.
Right. Yesterday, yeah. Yesterday was the last. Okay, Nidhi, thank you for joining. Kirtana also. So I'll end the class today.
Thank you, ma'am.